Download this code from codegive.com, link in the description below. Checksum error detection and correction, a comprehensive tutorial. Checksums are a fundamental error detection technique used in data transmission and storage to ensure data integrity. They provide a relatively simple way to verify that data has not been corrupted during transit or storage. While checksums are primarily used for detection, they can also be extended to perform some limited error correction. This tutorial will cover 1. The basics of checksums * understanding the fundamental principles behind checksums. 2. Types of checksums * common checksum algorithms like simple checksum, Fletcher's checksum, Adler 32 checksum, and CRC, cyclic redundancy check. We'll focus on simple checksum for code examples. 3. Checksum calculation * detailed explanation of how to calculate checksums. 4. Error detection with checksums * how checksums are used to detect errors in data. 5. Error correction, limited, with checksums * how checksums, with some clever implementation, can perform some limited error correction. 6. Code examples, Python practical Python code demonstrating checksum calculation, error detection, and error correction. 7. Limitations and considerations * discussing the limitations of checksums and when to use them. 8. Other error detection and correction techniques * briefly mentioning other techniques. 1. The basics of checksums. At its core, a checksum is a value computed from a block of data. This value is then appended to the data during transmission or storage. Upon receiving the data, the receiver recalculates the checksum based on the received data and compares it to the checksum received along with the data. Purpose to verify that the data received matches the data sent. Mechanism calculating a fixed size value, the checksum, based on the content of the data. Error detection if the calculated checksum at the receiver differs from the received checksum, it indicates an error occurred during transmission or storage. 2. Types of checksums. There are various types of checksum algorithms, each with varying degrees of complexity and error detection capabilities. Here are some common ones. Simple checksum * the simplest form of checksum. It involves summing all the data units, bytes or words, in the data block. The sum is then truncated or masked to fit within a fixed number of bits. Simple to implement but less reliable. Fletcher's checksum * improves upon the simple checksum by calculating two sums independently. It is more sensitive to errors, especially those that swap adjacent bytes. Adler 32 checksum * similar to Fletcher's checksum, but uses modulo arithmetic with two prime numbers. It is faster to compute and provides better error detection than simple checksums. CRC, cyclic redundancy check, a more sophisticated checksum algorithm based on polynomial division. CRCs are widely used because they offer excellent error detection capabilities for a relatively low computational cost. Common CRC standards include CRC 16, CRC 32. Hashing algorithms, MD5, SHA-256, etc. While strictly not checksums, cryptographic hash functions can be used for data integrity verification. They provide very strong error detection but are more computationally expensive. They are primarily designed for security, not just error detection. For the code examples in this tutorial, we'll primarily focus on the simple checksum due to its simplicity and ease of understanding. However, the principles apply to other checksum algorithms as well. 3. Checksum calculation. The process of calculating a checksum involves iterating through the data, performing arithmetic operations on each data unit, typically bytes, and accumulating a result. The final result is then often processed further to fit within the desired checksum size. Example, simple checksum, 8-bit. Let's say we have the following data, represented as a list of bytes. Data equals 0x10, 0x20, 0x30, 0x40, 0x50. The steps for calculating a simple 8-bit checksum are: 1. Initialization * start with a checksum value of 0. 2. Iteration * iterate through each byte in the data. 3. Summation * add each byte to the checksum. 4. Truncation, or masking if the sum exceeds the maximum value for an 8-bit integer, 255, truncate the sum to 8 bits, example using modulo 256 or bitwise and with 0xFF. This prevents overflow. In this example, checksum equals 0. Checksum equals 0 plus 0x10 equals 0x10. Checksum equals 0x10 plus 0x20 equals 0x30. Checksum equals 0x30 plus 0x30 equals 0x60. Checksum equals 0x60 plus 0x40 equals 0xa0. Checksum equals 0xa0 plus 0x50 equals 0xf0. The final 8-bit checksum is 0xf0, 240 in decimal. 4. Error detection with checksums. The process of error detection using checksums is as follows. 1. Sender asterisk calculates the checksum of the data. Appends the checksum to the data. Transmits the data and checksum. 2. Receiver asterisk receives the data and the checksum. Calculates the checksum of the received data using the same algorithm used by the sender. Compares the calculated checksum with the received checksum. 3. Error indication asterisk if the calculated checksum matches the received checksum, it is likely that the data was transmitted without errors. If the calculated checksum does not match the received checksum, it indicates that an error occurred during transmission. The data is considered corrupted and should be discarded or retransmitted. Important note: checksums are not foolproof. Certain types of errors can go undetected. For example, if 2 bytes are swapped and their values happen to sum to the same total value, a simple checksum might not detect the error. 5. Error correction, limited, with checksums. While checksums are primarily for error detection, they can be used for limited error correction in certain scenarios. This often involves adding redundancy and / or knowing the nature of possible errors. Here are a few techniques. Redundancy * break the data into smaller blocks and calculate a checksum for each block. If an error is detected in one block, you can request retransmission of just that block, minimizing bandwidth usage. This doesn't actually correct the error, but it improves efficiency in error recovery. Error correcting codes, ECC. More advanced checksum-like codes, such as Hamming codes or Reed-Solomon codes, are specifically designed for error correction. These codes add extra bits to the data in a way that allows the receiver to not only detect errors but also to reconstruct the original data, up to a certain number of errors. These are significantly more complex than simple checksums. Pre-known error scenarios. If you know the kinds of errors that are likely to occur, example a single bit flip, you can design a checksum scheme that is tailored to detect and possibly correct those specific errors. For example, you could use a checksum that includes parity bits for each byte. Example, simple error correction with parity, illustrative. Imagine your data is just a single byte. You add a parity bit, either even or odd parity. Let's use even parity. The number of ones in the byte plus parity bit must be even. Asterisk data, 7 bits 0101010, 3 ones. Asterisk even parity bit asterisk 1, adding this makes the total number of ones even, 4. Asterisk transmitted data asterisk 010101001. Now, suppose a single bit flip occurs during transmission, changing the data to asterisk received data asterisk 010100001, 2 ones. The receiver checks the parity. The number of ones is now odd. This immediately indicates an error. If you know that the error is always a single bit flip, you could attempt to correct it by flipping each bit in turn and checking the parity again. However, this is only feasible for very small data sizes and simple error models. Important asterisk this parity example is extremely simplified. Real-world error correction uses more sophisticated techniques like Hamming codes or Reed-Solomon codes that can correct multiple errors and don't require knowing the specific type of error. 6. Code examples, Python. Here are Python code examples demonstrating checksum calculation, error detection, and a limited error correction scenario using a simple checksum with a known error. Explanation of the code asterisk. Asterisk calculate underscore checksum, data, calculates the 8-bit simple checksum as described earlier. The N0xFF ensures the result stays within 8 bits. Asterisk detect underscore error, received underscore data, received underscore checksum, compares the calculated checksum of the received data with the received checksum to detect errors. Asterisk corrupt underscore data, data, bit underscore to underscore flip, simulates data corruption by flipping a single bit in the data. This is used to test the error correction. Asterisk correct underscore error, received underscore data, received underscore checksum. This function attempts to correct the error by trying to flip each bit in the received data one by one. For each bit flipped, it calculates the checksum and compares it to the received checksum. If they match, it means flipping that bit likely corrected the error. This is a highly simplified and limited example, useful only for demonstration. Asterisk the example usage demonstrates the entire process, calculating the checksum, simulating data corruption, detecting the error, and attempting to correct it. 7. Limitations and considerations. Checksums, particularly simple ones, have limitations. Asterisk limited error detection asterisk simple checksums are susceptible to errors that cancel each other out, example swapping bytes with compensating values. They are less effective at detecting burst errors, multiple consecutive errors. Asterisk no error correction, generally, checksums are designed for error detection, not correction. The error correction example shown above is highly limited and only works under very specific conditions. Asterisk computational cost asterisk while relatively inexpensive, checksum calculation does add overhead to data transmission and storage. Asterisk checksum length asterisk the length of the checksum affects its error detection capabilities. A longer checksum provides better error detection but also increases the overhead. Asterisk vulnerability to intentional modification asterisk checksums are not secure. They can be easily manipulated by someone intentionally trying to corrupt the data without being detected. Cryptographic hash functions should be used for security purposes. When to use checksums asterisk. Asterisk simple error detection asterisk when a basic level of error detection is sufficient. Asterisk low-cost solutions asterisk when computational resources are limited. Asterisk non-critical data asterisk when the consequences of undetected errors are not severe. Asterisk in combination with other techniques asterisk checksums can be used in conjunction with other error detection and correction techniques to provide a more robust system. 8. Other error detection and correction techniques. Asterisk parity bits. Asterisk adding a parity bit to each byte to ensure that the number of ones is either even or odd. Can detect single bit errors but cannot correct them. Asterisk hamming codes. Asterisk error correcting codes that can detect and correct single bit errors and detect some multi-bit errors. Asterisk Reed-Solomon codes. Asterisk powerful error correcting codes widely used in data storage, CDs, DVDs, Blu-ray discs, and communication systems. Can correct multiple errors and erasures, missing data. Asterisk forward error correction, FEC, a general term for techniques that add redundancy to data to allow the receiver to correct errors without requiring retransmission. Reed-Solomon codes are a common type of FEC. Asterisk ARQ, automatic repeat request, a protocol that uses error detection, example checksums or CRCs, and requests retransmission of data when an error is detected. Conclusion. Checksums are a valuable tool for basic error detection in data transmission and storage. While limited in their capabilities, they are simple to implement and provide a reasonable level of protection against common errors. For more critical applications, consider using more robust error detection and correction techniques such as CRC, Hamming codes, or Reed-Solomon codes. Remember to choose the appropriate technique based on the specific requirements of your application, balancing error detection/correction capabilities with computational cost. The simple example provided of error correction is purely illustrative. Real-world error correction is far more complex.